Let's talk about determination of molecular mass by osmotic pressure. Imagine you have a U-tube separated by a semi-permeable membrane. On the left-hand side of the membrane, you have pure solvent, and on the right-hand side, you have a solution. Now let's say you know the concentration of solution, but you don't know the molecular mass of solute. Right? Now, if you know osmosis, you know that when two solutions of different concentration are separated by a semi-permeable membrane, solvent molecules travel from a region of low solute concentration to a region of high solute concentration, right? Solvent molecules will move from a region of low solute concentration to a region of high solute concentration, which is your solvent to solution side. If you want to express the same thing in terms of solvent concentration, you would say that solvent molecules travel from an area of high solvent concentration to an area of low solvent concentration. Now, when this happens, when these solvent molecules travel from solvent to solution side, if you were to stop the flow of these molecules, what would you do? You would have to apply some pressure, of course. You'll have to apply some pressure on the opposite side. That means on the solution side. Now, in the beginning, when you apply a little bit of pressure, it would decrease the flow of solvent molecules a little bit. When you apply a little more pressure, the decrease would be a little more. There would come a point where you have applied enough pressure so as to stop the flow of solvent molecules altogether. If you apply any more pressure, reverse osmosis would happen. That means solvent molecules will then travel from solution to solvent side. But the pressure that just stops the flow of solvent molecules, or that just stops osmosis from happening, is called as osmotic pressure and is denoted by the letter pi. Now, can we use this osmotic pressure to find out molecular mass of solute? Yes, we can. And here's how. So the osmotic pressure is directly proportional to concentration of the solution. Higher the concentration gradient, more will be the flow of solvent molecules, more pressure would be required to stop the flow of these solvent molecules. In the same way, it's also directly proportional to temperature. Higher temperature, more kinetic energy in solvent molecules. More kinetic energy means more movement, and therefore more pressure would be required to stop this movement. Right. So when we remove this proportionality sign and replace it with equal to sign, a constant appears. And here the constant is R, your gas constant. Now we'll have to expand this relationship a little bit. Concentration here is expressed in molarity. So that can be written as moles of solute divided by volume, total volume of the solution. R and T remain as such. Moles can be further written as mass of the solute, the given mass of the solute in the solution, divided by molar mass of the solute. Everything else remains as such. So here, this is the relationship that you can use to find out molecular mass of the solute. But you'd have to be a little careful about the units. Temperature has to be in Kelvin. Volume has to be in liters. W2 has to be in grams. And value of R would depend on actually unit of osmotic pressure. If you express osmotic pressure in atmospheres, the value of R would be 0.0821 atmosphere liters per mole per Kelvin. And if you express osmotic pressure in bars, the value would then be 0.0831 bar liter per mole per Kelvin. And when you work out the unit, you will see that the unit of molecular mass comes out to be grams per mole, which is as it should be. Now, let's use this relationship to solve a problem. So the problem that we have is the osmotic pressure of a benzene solution containing 2 grams of polystyrene per liter was found to be 0.01 atmospheres at 27 degrees Celsius. Find out the molecular weight of the polystyrene. So let's use the relationship that we have. Pi given is 0.01 atmosphere. equals to weight of the solute given here is 2 grams times, since our unit here is the atmosphere, we will use 0.0821 atmosphere liters per mole per Kelvin. Temperature is given in degrees Celsius. We'll convert that into Kelvin. 27 plus 273 gives us 300 Kelvin. Molecular mass is what you have to find out. Volume given is 1 liter. Now, when we solve for molecular mass, what we get is 4926 grams per mole. See, the unit also works out. Atmosphere, atmosphere cancels out. Liters, liters cancel out. Kelvin, Kelvin cancels out. What you are left with is just grams per mole. Now, osmotic pressure is not the only method that we use to find out molecular mass of solute. We have other methods as well. We have elevation in boiling point, we have depression in freezing point, and relative lowering of vapor pressure. But osmotic pressure method has two main advantages over the other methods. As you can see, in all these methods, the property is indirectly proportional to molecular mass, which means in case of macromolecules where the mass is high, the value of the property becomes low. Now, in case of these three properties, that is a problem, because here what we measure is a difference. Difference in boiling point, difference in freezing point, difference in vapor pressure, which is already a small value. And when molecular mass of solute is high, this becomes an even more smaller value, which would be difficult to find out. But that's not the case with osmotic pressure, because in case of osmotic pressure, what we measure is an absolute value. So even if your solute is a macromolecule, the value of osmotic pressure would still be considerable and you would still be able to find it out. The next main advantage is that measurement of osmotic pressure takes place at room temperature. Now, which is beneficial, especially if you have biomolecules, because biomolecules are temperature sensitive. If you use a property which makes the measurement at a very high temperature or at a very low temperature, biomolecules may get denatured or may get inactive, right? So with those molecules, with those solute, it's best that we use osmotic pressure method to find out the molecular mass of the solute. So here you go. These two advantages make osmotic pressure a preferred method to find out molecular mass of solute.